Yeah, so I have to apologize. I was streaming and then suddenly the stream died and I didn't know why and I lost internet, but it was very brief. So um, it should be working now. And on my end it's saying that the stream is healthy. Anyhow, let's just get started. There's only a couple of you in the one little lecture that I did, which was just the calculus based stuff for um, the RC circuits, the RL circuits, and the LC circuits. Okay, so let me just very quickly remind you of what those circuits. Put this up online, and not just the video, but also the notes up online. Okay, if you have any questions, then just chat them in the put them in the chat there, and I'll look over at the chat every once in a while and make sure that I answer them. Okay, so what we're looking at right now is the lecture for the notes for the lecture for April 27th, and I don't want to go over that all because I went over it already. But let me just show you a couple of the important formulas here. Okay, so one of the first one of the first circuits we looked at was the RC circuit, and for the RC circuit, this is a resistor and a capacitor in series. There is no battery, okay? And so in order for this circuit to work, you have to charge up the capacitor, and then basically the charge in the capacitor, that's Q as a function of time, is going to be some original charge, like charge at t equals 0, multiplied by this exponential decay, where the time constant, the time constant here is just r times c. Okay, and so then it exponentially decays. Well, I mean, I did prove that by simply saying, look, you've got a resistor and a capacitor, and the potential drop across the two has to equal 0. Why 0? Because there's no battery. Okay, and then just plugging in Ohm's law there, and for the potential across the resistor, I'm plugging in the definition of capacitance there, that is the voltage drop across the capacitor in terms of the charge in the capacitor, the capacitance of the capacitor. Ask with that. Well, the question that I could ask is actually currents through this particular circuit. If you take a look through here, there's I, and you go, well, I don't see any I in the solution. That's right, there is no I in the solution, but there's this. So we can actually ask in an RC circuit, not just what charge is on the capacitor, but we can also ask what currents are traveling through the circuit. Okay, and so that's like a modification or an additional kind of question that I could ask about RC circuits that I can't ask, say, for the non-physics students, but I could ask for you guys. And we'll do a problem like that. It's pretty easy, okay? So don't get like all freaked out about the fact that this is really get much out of those except just plugging in numbers. But we will look at the RL circuit, and for the RL circuit, that's the circuit which is a resistor and an inductor in series. And again, I've got no battery here. And you say, well, how does the current get going in this thing? Yeah, well, you have to prepare a current, okay? So, like not drawn in the circuit right now. Somehow I got a current going in here. And once the current is going, the inductor wants to keep the current going. That's the whole thing about an inductor. They use magnetic fields to try to resist changes in current. So the L tries to keep pushing the current. But of course, the resistor keeps dissipating away the energy, so the current will eventually decrease. If there really were no resistance in this wire at all, then the inductor would just keep the current going at the same rate all the time. Okay, now let's look at that one. Again, you start with the fact that the potential drop across the resistor and the potential drop across the inductor are 0. Okay, and from that you can use the definition of, or use Ohm's law for the potential drop across the resistor. Use this equation, which is the definition of the inductance. Okay, that's L is the inductance for the potential across the inductor. Okay, and then plugging that into the equation that says that the potential drop across both must be 0. Again, 0 because it's no battery in there. Well, then you can just solve for the differential equation, and it turns out that this is the equation that solves it. Okay, which looks an awful lot like the previous one, except that I replaces Q. Okay, and there's a derivative in there. And again, this is an extra question that I can ask because you guys have calculus, but the physics 112 don't. Okay, so that's what we're going to be looking at. And let me just look in the chat here. All right. So in these problems, because I didn't do it in the theory, and I don't want to overdo these problems because you know, you guys are probably not going to head down the road of being physics majors. So there's no need to look at all the variations on these circuits, like with the batteries and without the batteries. We're just going to look at the situations where there is no power supply in these problems, okay? So somehow the circuit has been prepared, okay? And let's look at the RC circuit first, all right? And so questions 1 and 2, you should be able to do. It's question 3, which is the new one, all right? So I give you a 30 microfarad capacitor, and I'm going to charge it up to 100 microcoulombs, all right? And I'm going to allow this capacitor to discharge through a 10 kilo ohm resistor, okay? And the equation which governs this is this one. Now, we saw that a minute ago, but, you know, here it is in this app, which is e to the minus t, that's how long you wait, divided by tau. And tau is a characteristic time of this circuit. It's the time constant, and it's just r times c like that. And so the first question is, what is the time constant? And that's easy, no calculus there. Okay. And then what is the charge on the capacitor after 1 second? Also no calculus there, so just plugging in. This is the interesting one. So I have here, how do you do this? How do you do what is the current through the resistor after 1 second? Okay, because there's no current in here, but there is implicitly, because the first derivative of the charge as a function of time, that is the current. Okay, so let's begin answering this. So the first one, what is the time constant? Well, tau here is equal to RC, and R is going to equal, R is the 10 kilo ohm, and C is the 30 microfarads here, like that. Okay, and we have to do this in MKS. So this is 10. The K, so ohms is the MKS unit. So K is, we have to turn that into an exponent, a power of 10. So K is 1,000, and that's in ohms. All right, and then micro. So what's a micro? Micro is a millionth, 10 to the minus 6, like that, and that's farads, like this. All right, and what's that going to equal? It's going to equal 100 times 300 times 30 is 300 times 10 to the, and it's going to be plus 3 minus 6 is minus 3, like that. And an ohm times a farad, go, what kind of a unit is that? Remarkably, and it has to come out to seconds, but remarkably it's seconds. And it has to come out to seconds because the ratio of those two has to be a dimensionless number. So the seconds on top have to cancel the seconds on the bottom. So this is going to be 0.3 seconds, like that. Okay? So make sure I did that right. Let's see, we have a 10 times 30. Yeah, looks okay. All right, so that gives us the time constant. Now, how much charge is on the capacitor after 1 second? That's this equation right here. Okay, and we can start to plug in. Q naught, that is the charge on the capacitor at t equals 0, and I told you that's 100 microcoulombs. And we'll just work the whole problem using microcoulombs. Okay, and then e to the exponent, and it's minus, and how long are we waiting? We're waiting 1 second. So the t here, that's 1 second, but the tau turned out to be 0.3, and you have to work this out on your calculator. So let me see here, e to the exponent -1 divided by 0.3 multiplied by 100. It turns out to be, actually rounding off, and microcoulombs. Okay, so that was easy enough, and no calculus yet. It's when we get to this point that the calculus comes in. So I say, what is the current through the resistor at that time? And the current in this entire circuit is dq by dt, like that. Okay. Now you might say, but isn't Q, the charge on the capacitor, and we're asking for the current through the resistor. Yeah, but the current through the capacitor and the current through the resistor have to be the same. Why? Because they're in series. Okay, that's almost like a defining property of series, is that the charge has to be the same. Okay, so let me look in the chat here if there's any questions. I don't see any. So how do you do this? Well, I actually have this worked out in my notes. Okay, well, you know what? It doesn't take much to switch back. Let me switch back to this, and where do I have it here? Here it is. Okay, there's the equation for the current in terms of dq by dt. And also, if you look at the circuit itself, R and C are in series, so whatever the current is through one, it has to be the same current through the other. Okay. Okay, wait. There's a question. Should we be using MKS for all the problems on the final? Yeah. I would say yes and no. I mean, when you plug into the equations, work in MKS. But of course, the answers, I might move the decimal over and switch to some metric prefix. Okay, so you know, it's the usual kinds of things you've seen on the on my my tests, where the answer might come out to be, I don't know, just to pick a number like 3 times 10 to the minus 3 meters. Well, 10 to the minus 3 is 1,000th milli, and I might, instead of writing 3 times 10 to the minus 3, I might write 3 millimeters, okay? So work in MKS, but then the final answer, I may switch to, using some metric prefix, okay? So, well, there it is, all right? So, okay, let's switch back to this here. And whoops, I was going to show you one other thing, and I got sidetracked answering your question. Not that that's a problem, but let me just show you here. There was the this here, the I is equal to dq by dt. The dq by dt, if you actually work it out, it just turns out to be minus 1 over tau times q. And you say, well, why does that happen? Well, because when you differentiate the exponential, you get the exponential back again, but with this extra minus t over tau, okay? And so, I put it all together. I is equal to dq by dt, but dq by dt, that's just equal to minus 1 over tau times q. Okay, so just remember this equation here. I'm going to write it minus, let me switch back to the whiteboard. Oh, I've lost the whiteboard. Hold on here. There we go. Okay, and make sure the whiteboard comes back up. Okay, so over here, this is the equation that you just saw, like that. So I is equal to dq by dt, but dq by dt, if you differentiate the exponential, you get the exponential back again with the minus 1 over tau, like that. And so it's as easy as just plugging into this, all right? And you might have even been able to figure that out by reading the notes, but like, it's good to see this at least once worked out for you. Okay, so that's going to give you the current. So that's minus, and it's 1 divided by 1.3 per second. I'll even leave the units in there, and because you'll see what happens. And then this is the current, sorry, the charge after 1 second. Okay, so what is the charge on the capacitor after 1 second? What is the current after 1 second? Well, the current is basically the charge after 1 second divided by tau. Okay, and so don't worry about the negative sign. I'll explain that one in a second. So what's this going to work out to? 3.57 divided by 0.3 equals 11, negative 11, and it's going to be microamps. Okay, like that. All right, and so the negative just means that the current is traveling in the opposite direction of the decreasing of the charge. Okay, so there it is. Okay, and now back to Corey's question. Like in here, instead of that micro, let me just write this on another line here. Oops. All right. Instead of the micro there, I could have said, well, micro is times 10 to to the exponent -6. And then over here, I would have gotten times 10 to the exponent -6 amps, like that, okay? But on the test, I generally wouldn't do an answer like that. I would see the times 10 to the -6 there and convert it to micro, okay? So there was the first one, all right? Let me see if there's any questions in the chat. Nope, not seeing any questions. Let's do an RL circuit, okay? So here's an RL problem. So let me remind you what the RL circuit looks like. All right. So an RL circuit basically looks like this. It's an R and L in series. And once a current is going in this circuit, the inductor wants to keep it going, but the resistor wants to dissipate that energy. And this equation is solved or is described by the current is equal to an initial current multiplied by an exponential decay. All right. And if you take a look at the solution to this, it looks like this. There's the solution right there. If you plug that in to our equation, you can see that it works, okay? And we're going to make use of this in a second. So notice that we, at some point, have to make use of di by dt here, like that. And di by dt turns out to equal just 1 over tau times I. Actually, there's a minus in front here. I noticed it later that I made a mistake in my notes. This should be actually minus 1 over tau I times I, like that. Okay, so let's do the problem, and you'll see when I make use of this fact. Okay, in solving the problem. All right, so let's switch back to the whiteboard there. All right, and we have here a 30 microhenry inductor. Has 100 milliamps of current passing through it. Okay, so somehow I've prepared my inductor with some current passing through it. The current also flows through a 10 kilo ohm resistor, and then I answer these questions. What is the time constant? What is the current through the inductor after 1 second? And what is the potential drop across the inductor after 1 second? It's number 3 that is a little bit different than the previous one, because in the previous one we had a current, and here we have potential drop, okay? And you say, well, what's the relationship between potential drop and current? Well, you'll see that when I get there. So let's solve the problem. So the first thing is, what is the time constant? Well, for an LR circuit, the time constant is given by L divided by R, like that, okay? And so we have the inductance, which is 30 microhenries, like this. And the resistor is 10 kilo ohms, like that. All right. And let's work very carefully in MKS, and then if we have to, we can change. We won't have to, but if we do, we know we can change, add metric prefixes afterwards. Micro is 10 to the -6. Okay. And kilo here. Kilo right there, we're going to replace that with times 10 to the exponent 3. Okay, so again, micro is 10 to the -6, and kilo right here is 10 to the 3. And if we work this out, so 30 divided by 10, that's 3. And 10 to the -6 divided by 10 to the -3 is actually times 10 to the -9 seconds. Okay. So very different number than above. Okay, above we had only 0.3 seconds, but here we have 10 to the -9 seconds. And you might see that on a test as, what's 10 to the -9? Nanoseconds. Okay, so the time constant here is 10 nanoseconds. And you know what? I better change I said after 1 second. No. We're going to do what is the current through the inductor after 1 nanosecond. Okay, so there we go. What's the time constant? Tau is equal to L over R. That's the 30 microhenries divided by 10 kilo ohms. Micro is 10 to the -6 right there. So it's 30 times 10 to the -6 henries. Divided by 10 kilo ohms is 10 times 10 to the 3 ohms. Okay. And I just did, you could do this in your head. You just do 30 divided by 10. That gives you 3. And then you do 10 to the minus 6 divided by 10 to the 3. That's minus 6 minus 3, so that's minus 9. So it's 3 times 10 to the minus 9, and that's going to give you the 10 to the minus 9, that's going to give you a nanosecond. Okay, so 3 nanoseconds. So what's the current passing through the inductor after 1 nanosecond? Well, it's just this equation right here. Okay, and it's as simple as plugging in the numbers. What's the original current? Well, the original current is 100 milliamps. Okay, and now this isn't an MKS, but that's okay, because if I work in milliamps here and I just keep the milliamps there, then the answer will come out in milliamps. Okay, it's when you have things that divide and stuff like that, the units are better work out. So you know, here the units have to be seconds, and there the units have to be seconds, and indeed there. Okay, so here it's going to be e to the exponent negative, and t, we're waiting 1 nanosecond. Okay, divided by the time constant, which is 3 nanoseconds. Okay, and the nanoseconds on top and the nanoseconds on the bottom, they're going to cancel right in there. Okay, and what's that going to equal? Well, let me do it on the calculator. It's going to be, what is it going to be? E, so it's 100 multiplied by e to the exponent negative 1 divided by 3. Close bracket. All right, looks like here's the number, and let me get rid of some of these too many decimals like that. Okay, and milliamps. All right, let's see, does that make sense? Before I go any further, it starts off at 100 milliamps. Okay, and if there were no resistor, it would stay at 100 milliamps. But there's that resistor that's eating away the energy. Okay, and so after 1 nanosecond, we're down to 71.7 milliamps. Okay, so now what? Well, oh, I lost it again. It seems to happen whenever I switch screens. Okay, now what? Well, let's take a look at the last question. What is the potential drop after 1, and that should be 1 nanosecond. All right, 1 nanosecond like that. And well, let's take a look at potential drop here. All right, so if we go back to our notes, and you take a look at what the potential drop is across an inductor, the potential drop across an inductor is the inductance L multiplied by di by dt. Okay, so remember that equation. I'm just going to type it very quickly. BL is equal to L times di by dt, like that. Okay, and just typed it into the whiteboard. And now what's that di by dt equal to? Well, when you differentiate the exponential, you get the exponential back again. And so it's not hard to see that di by dt just turns out to be minus 1 over tau times I. Okay, and again, maybe I should just show you very quickly why that happens. You see, if you have I naught e to the minus t over tau, when you differentiate the right-hand side here, well, the I naught comes in front. The derivative of the exponential is the exponential again, and then you get, because of the chain rule, you get the minus 1 over tau. Okay, and then you recognize that I naught e to the minus t over tau, that's just I all over again, and you get this equation here for, with the minus sign in front, for di by dt. Okay, so let's switch back now to the whiteboard. All right, and so over here, we had that VL, that's the potential drop across the inductor, which is what I'm asking you for. That's going to equal the inductance times di by dt. Whoops, that's a lowercase t, like that. And there's L in front, okay? Now, what's that di by dt? Maybe I should just do that in a separate line, okay? Di by dt, we just determined that was, see, look at what it was up here for dq by dt. It was this, okay? It's the exact same thing, only instead of q, it's I, because they have both equations have the same structure, with q replacing, or with I replacing q. Okay, and now you say, well, do I know I the current after 1 nanosecond. Do you know the current after 1 nanosecond? Yeah, you do. It's this. Okay? And so we'll be able to use that in here, get this, and then multiply it by the inductance and get the potential across it. Okay? So let's just put the two equations together. I've got this, and then over here, I've got this. Okay? And the negative sign is just direction, so it's not that interesting, okay? I'll leave it in there, but it's not that interesting, okay? And now we can just plug in the numbers. What's L? L is the inductance, okay? So that's the 30 microhenries, like that. Okay. And then over here, we have 1 over tau, all right? And that's 1. I'm just gonna, you know what? I'm gonna just drop the negative sign so it doesn't cause any confusion. So there's the 1. So there's the L, 30 microhenries. There's the 1 over tau. It's 1 divided by 3 nanoseconds. Okay. Or sorry, no. 3 times 10 to the minus 9. Okay. Microseconds. So there we go. There's seconds. All right. And I is going to be this, like that. And you know what? Let me do this systematically, show you how the units work. To be very, very careful. Okay. So what I did was I just plugged in everything with the units the way they are, not necessarily MKS. And on the next line, let me switch everything to MKS. Okay. So that 30 microhenries, the micro, times 10 to the minus 6, okay? And then we have over here 1 divided by 3 nanoseconds. All right. What's a nano? Times 10 to the exponent negative 9, like that. Whoops, the seconds should go in the brackets. There we go. Seconds, I'll get it. Okay. And then finally, we have this, the 71.7 milliamps, and milli is times 10 to the minus 3. Okay? And now everything is in MKS here. I'll even label it. All MKS units. Okay? And now you're guaranteed that whatever you get on the next line is going to be MKS. All right? So, it looks a bit ugly. How can I make this nicer for you? It'll be volts, okay? Let me maybe do this. All right, because that's in the numerator. Just trying to make this look as nice as possible. It'll be this because that's in the numerator, okay? And that tau here, so the 1 over tau, that's in the denominator, like this, okay? And you say, where did the units go? It's all volts, right? How do you know it's volts? Well, because it's a potential. And if all of these are MKS units, then you're guaranteed that that's going to be volts there like that. All right? Now what? Well, now we just put this in our calculator. So I'm going to do 30 times 71.7 and then divide it by 3. So that's 10. Oh, I could have done this in my head. 10 times 71.7. So that's the 30 times that divided by 3. And now to get the exponent right, what do I have? Well, I'll just show you what I do. It's like minus 6 right there, right? Whoops. That should be a bracket. So I've got minus 6 there, okay? And then I've got minus 3 there, okay? And then I'm dividing by 10 to the 9, so it's going to be plus 9 there like that, okay? And 6 minus 3 plus 9, well, what does that equal to? 0. So this is going to equal 717 volts. And there's your answer. Okay? So there you go. There's the potential drop. So the potential drop, the reason this involved the calculus was because the way you relate the potential to the current is by the first derivative. Okay? But it's not very hard because I did that first derivative for you. That first derivative is basically just equal to current divided by tau. Okay? Actually, you could even write this, like that's the way I wrote it in the notes, but you could even write this as just I of t, or here's a better way. I divided by tau. That's about as easy as I can write that, okay? So if you've got the current already, and you do from the previous question, you just divide it by tau, and boom, you've got your answer. And the negative sign is just a direction, okay? So you don't even need that. And you know what? The same thing up here for the capacitance, where I have the current, and current is dq by dt. I don't know why we have these spaces there. It'll look a little better. And so that's the way I wrote it. But you know what? You could just write that as very simply as just q, or negative q divided by tau. Okay? So if you have the charge divided by tau, and you've got the current. Okay? Do that on the next line as well. All right? So there you go. So this is just basically your RC circuit and your RL circuit. And I won't do the LC circuit, any calculus for the LC circuit, okay, because it's just sinusoidal motion. But this question number 3 here, for both of them, that's something that's beyond what you can do without calculus. And so I just thought I'd give you this extra little lecture in addition to all the stuff that you saw from the review session that I originally did with Physics 112, and I left that up online for you guys to look. I think I did 10 questions there, or maybe even more. In addition to all those questions, these are the kinds of questions that you might see as Physics 102. Okay, let me see if there's any questions in the chat. All right, so any questions? If not, this is it. You know, it doesn't, I didn't need to do a lot here. It's just that I wanted to separate this material from the previous material, because this material involved calculus and the other one didn't. All right, so I'll just wait a second, and if there are no questions, then I know it isn't time up yet, but this is all I really wanted to cover today. All right, not seeing any questions. I'll put both this note and a link to this video on our Moodle site, and then you can refer to it later. All right, guys, bye-bye.